Light emitting diodes (LEDs) have revolutionized the displays industry. LEDs use electric current to produce visible light without the excess heat found in traditional light bulbs, a glow called electroluminescence. This breakthrough led to the eye-popping, high-definition viewing experience we have come to expect from our screens. Now, a group of physicists and chemists have developed a new type of LED that utilizes spintronics without needing a magnetic field, magnetic materials, or cryogenic temperatures, a quantum leap that could take displays to the next level. The companies that make LEDs or TV and computer displays don't want to deal with magnetic fields and magnetic materials. It is heavy and expensive to do it. Most optoelectronic devices such as LEDs only control charge and light, and not the spin of the electrons. The electrons possess tiny magnetic fields that, like the Earth, have magnetic poles on opposite sides. Its spin may be viewed as the orientation of the poles and can be assigned binary information. An up spin is a 1, a down is a 0. In contrast, conventional electronics only transmit information through bursts of electrons along a conductive wire to convey messages in ones and zeros. Spintronic devices, however, could utilize both methods, promising to process exponentially more information than traditional electronics. One barrier to commercial spintronics is setting the electron spin. Presently, one needs to produce a magnetic field to orient the electron spin direction. Researchers from the University of Utah and the National Renewable Energy Laboratory developed technology that acts as an active spin filter made of two layers of material called chiral two-dimensional metal halide perovskites. The first layer blocks electrons having spin in the wrong direction, a layer that the authors call a chiral-induced spin filter. Then, when the remaining electrons pass through the second light-emitting perovskite layer, they cause the layer to produce photons that move in unison along a spiral path rather than a conventional wave pattern to produce circular polarized electroluminescence. The study was published in the journal Science. The scientists exploited a property called chirality that describes a particular type of geometry. Human hands are a classic example. The right and left hands are arranged as mirrors of one another, but they will never perfectly align, no matter the orientation. Some compounds such as DNA, sugar, and chiral metal halide perovskites have their atoms arranged in a chiral symmetry. A left-handed oriented chiral system may allow transport of electrons with up spins but block electrons with down spins and vice versa. If we try to transport electrons through these compounds, then the electron spin becomes aligned with the chirality of the material. Other spin filters do exist, but they either require some kind of magnetic field or they can only manipulate electrons in a small area. The beauty of the perovskite material that the researchers used is that it is two-dimensional. Metal halide perovskite semiconductors are mostly used for solar cells these days, as they are highly efficient at converting sunlight to electricity. Since a solar cell is one of the most demanding applications of any semiconductor, scientists are discovering other uses exist as well, including spin LEDs. The researchers say they are exploring the fundamental properties of metal halide perovskites, which has allowed them to discover new applications beyond photovoltaics. Because metal halide perovskites and other related metal halide organic hybrids are some of the most fascinating semiconductors, they exhibit a host of novel phenomena that can be utilized in transforming energy. Although metal halide perovskites are the first to prove the chiral hybrid devices are feasible, they are not the only candidates for spin LEDs. The general formula for the active spin filter is one layer of an organic chiral material, another layer of an inorganic metal halide such as lead iodide, another organic layer, inorganic layer, and so on. The concept proves that using these two-dimensional chiral hybrid systems gain control over spin without magnets and has broad implications for applications such as quantum-based optical computing, bioencoding, and tomography.